Okay, this is Chapter 13, Fundamentals of Electrochemistry. We're first going to start off, what is electrochemistry? And it is considered the use of electrical measurements of chemical systems for analytical purposes, i.e. getting an equilibrium constant, um, using electricity to drive a chemical reaction, such as electrolysis or electroplating. It's also using a chemical reaction to produce electricity, like the batteries in your phone, your computer, or your car, or in some fuel cells. So first we're going to start off with a couple terms. Current is the charge flowing each second through a circuit. It's found in units of amperes, and that's also equal to 1 coulomb per second. Um, you'll find later in this presentation, electric potential is the work needed when moving electrical charge from one point to another through a circuit. They're found in units of volts, and the higher electrical potential you have, the greater the push, the more work you can do with that potential. Okay, so this chapter is chock full of different equations you can utilize to determine which way a reaction is going to flow, how the electrons are going to flow, and this equation is just the beginning. This equation shows us that Q equals NF, where Q is the charge in coulombs, N is the moles of electrons in the species or reaction you're using, and F is Faraday's constant, which is 9.649 times 10 to the 4th coulombs per moles of electrons. And one electron has a charge of 1.602 times 10 to the negative 19 coulombs. So another big part of this chapter is the idea of work. Work is any time when charge, Q, moves through a potential difference, E, and the work done is calculated by the equation work equals E times Q. And under that, you'll see that work is found in units of joules, and that is equal to volts, which is the electrical potential, times coulombs. And for any spontaneous chemical reaction, the work done on the surroundings is going to be equal to the negative delta G. We see that delta G is equal to the negative NFE, where N is the moles of electrons, F is Faraday's constant, which you saw in the past slide, E is obviously your electrical potential. And this equation shows us that potential energy, or E, is directly proportional to Gibbs free energy. Okay, so now we're going to talk about Ohm's law and the term power. So Ohm's law states that current is directly proportional to the potential difference, or the voltage, but it's inversely proportional to the resistance of a circuit. Shown below is the equation I equals E over R, where R is resistance, and it's found in units of ohms. Power is the work done per unit of time, and it's measured in joules per second. So the major part of this chapter is all based around galvanic cells. Now, a galvanic cell, or voltaic cell, as some people would like to call it, uses a spontaneous chemical reaction to generate electricity. Now, it has two requirements. The first being that one of the reagents has to be oxidized and the other has to be reduced, and more on that later on. The second requirement is the two reagents cannot be in direct contact with each other. They have to be totally separate from each other and allowing some current to pass between them. So galvanic cells require an oxidized reagent and a reduced part of the reaction. These are called redox reactions, and they are comprised of two half reactions, as shown on the left-hand side. And there is a potential or voltage associated with each of the half cells. And we can use those numbers to predict the voltage from the whole cell when they're combined. In a redox reaction, there is a constant flow of electrons, electrical current, and that current is directly proportional to the rate of the reaction. So a little way some people like to remember how redox reactions occur is by the mnemonic device of Leo says Gur. Leo is losing electrons, and that's considered oxidation. Gur is gaining electrons, and that's considered reduction. In a redox reaction, there is an oxidizing agent, and that species takes electrons from another species and itself is reduced. A reducing agent is considered a reductant, and it gives electrons to another species and itself is oxidized. Okay, so now we're going to talk about the real-world idea of an anode or cathode as part of an electrochemical reaction. So as shown in this picture, your oxidation occurs at the anode, which is on your left-hand side. Electrons will then flow up through the circuit onto the right-hand side, which is the cathode, and that's where reduction occurs. And electrons will always flow from the anode to cathode no matter what you do. You can't go from the cathode to the anode, it's just not possible. So another part of this circuit is found at the top. and that's either called a voltmeter or a potentiometer. This measures the potential of the cell to do work. When electrons flow into this negative terminal on the left-hand side, the potentiometer reads a voltage that is positive. Another main part of any galvanic cell is the salt bridge. Now, the salt bridge is found directly in the middle of the system. It's seen as a tube connecting the two beakers of solution. Now, the salt bridge separates the two halves of the galvanic cell, and it forces electrons to go through the circuit instead of between the two. It's typically a U-shaped tube filled with some kind of gel. In this case, it's filled with KNO3 or some other kind of inert salt. And it's at each end capped with a semi-permeable membrane that allows ions to pass between the two solutions. These ions will migrate through the salt bridge to offset the charge buildup in each of the two beakers. So some of you might be asking, what happens if we remove that salt bridge? Well, the answer is pretty much nothing. It's considered a short circuit, and no electrons will actually flow through that circuit, resulting in no voltage or electrical potential being registered on the potentiometer. So electrochemical cells or galvanic cells can be written out in a number of ways. One way is line notation, and this entails single and double vertical lines, and the single line indicates a phase boundary. And shown below in a reaction of cadmium solid in circuit with a silver solid with silver chloride and cadmium chloride in solution. This is similar to electroplating. We see that the cadmium solid and the silver solid are separated by a phase because they're in solution, and those are separated by single vertical lines between the cadmium chloride and the silver chloride. So the other part to line notation is the double vertical line. Now, the double vertical line indicates the presence of a salt bridge, or a two-phase boundary. In the same reaction between cadmium solid and Ag solid, there's a salt bridge in between the two solutions. The single vertical lines denote the phase boundary in between the cadmium solid and the solution that the cadmium is in. The double line indicates that there's a phase boundary, two-phase boundary, between the two solutions that the cadmium and silver are in. And then finally, one last single vertical line that shows us that the silver solid is in the solution of silver nitrate. So another major section for understanding how electrochemistry works is the standard reduction potential, otherwise known as E naught. Now, standard reduction potential is measured for each of the half cells by matching that half cell with the standard hydrogen electrode, or She, whose potential was set at an arbitrary reference point of 0. And in this case, standard simply means that all activities are 1. But as we all know, it is almost impossible to make a cell where the activity is 1. So this is considered the ideal circumstances. When the standard reduction potential is calculated, you'll get a number that's either positive or negative, as with any number. When E naught is positive, this means that the electron flow from the standard hydrogen electrode to the other half cell is flowing as normal. The more positive this E naught is, the stronger of an oxidizing agent that species is. If E naught has a negative value, the electron flow is considered from the electrode to the standard hydrogen electrode opposite the positive. So it's moving in the opposite direction of the positive. And a more negative E naught means that the species is a worse oxidizing agent than the other. So in addition to measuring or calculating the standard reduction potential, we can also calculate the potential or voltage of a cell. And that is simply the difference between the two half reactions or half cells. And in a later slide, I'll show you exactly how to calculate the potential of a cell and a half reaction. So now I'll show you how to actually calculate your E naught value for a specific equation. Now the equation below, we see iodine solid is on the left, and we have a bromine solution in water, and that's reacting to form the products. Below in step 1, we see the two half reactions that are part of this full reaction. We see the bromine aqueous and its 10 electrons it's losing to form the 10 moles of bromine minus. And that has an E naught value of 1.098 volts, And the second half reaction is found below, and that has a standard reduction potential of 1.21 volts. Now we have to determine which half reaction must be reversed to fit into the original reaction equation. And we have to subtract that value from the other half reaction's E naught value. And now we see that the second half reaction has to be reversed in order to fit what the original reaction showed. So we're going to subtract the first half reaction's E naught value from the second half reaction's E naught value to get a negative 0.112 volts. Now this negative means that the reaction will proceed spontaneously in the reverse direction, not the forward direction, as we might see in some other reactions. So now we've just calculated our E naught values. Now we'll calculate the voltage of a standard lead acid battery. The equation above is given to you. It's a standard lead battery. And we find the half reactions for the anode and the cathode in Appendix H of Harris's quantitative chemical analysis. We find that the two half reactions, PbSO4 solid, losing 2 electrons to produce Pb solid and a sulfate, and the second half reaction, and both of them have a negative 0.355 volt E naught value. The cathode, which we found also, has an E naught value of 1.685 volts. Now, in order to calculate the voltage of this battery, we take the E naught value of the cathode and subtract the E naught values of the anode to result in a 2.04 volt result for this lead acid battery. So now I'll just recap what we've learned about the standard electrode potential. E naught potential is relative to the standard hydrogen electrode. It also refers only to the reduction reaction. E naught is independent of the number of moles of reactant and the products in the balanced half reaction, so it doesn't change no matter what you do with the reaction. E naught is also temperature dependent. E naught measures the relative force that tends to drive the reaction. And positive value of E naught indicates that the reaction proceeds spontaneously in the forward direction with respect to that standard hydrogen electrode. So now we've gotten some of the terms and definitions out of the way. Now we'll talk about the Nernst equation. And the Nernst equation is essential to any electrochemical species or reaction. And basically the Nernst equation gives the relationship between the cell potential and its concentration of the cell components. And it gives us the driving force for any electrochemical reaction. Now the Nernst equation is dependent on activity, which is simply the activity coefficient times the concentration of whatever species. The Nernst equation is given as E equals our E naught value minus RT over NF, where R is the gas constant, T is your temperature in Kelvin, N is the number of electrons in the particular half reaction that we're talking about, and F is Faraday's constant, which we saw in the previous slides. That is multiplied by the natural log of the activities times the concentration of the species we're talking about. So obviously the Nernst equation is a pretty long one, sometimes hard to remember exactly where everything goes. So as any good scientist does, we simplify that to be at room temperature, or 25 degrees Celsius. So the simplified Nernst equation is simply the E naught value minus 0.05916 volts over N times the log of the activities times the concentration for the species in question. And this equation is only to be used at 25 degrees Celsius, or the average room temperature, and we've just simplified the R and T values on the top. So now we'll look at how we actually set up the Nernst equation. And for this one, we're seeing zinc 2+, and it's losing 2 electrons and going into zinc solid precipitate. And this is an individual half reaction for a more broader full reaction. Now we see Q is equal to 1 over the concentration of zinc 2+, and we can plug that into Nernst, where we have our E naught value of negative 0.762. We plug that in, and we subtract the simplified Nernst, which is 0.05916 volts, over the amount of electrons, which is 2. And then we take the log of 1 over the concentration of the zinc 2+ solution in this half reaction. In this case, we don't have to balance the half reaction, or we don't have to multiply the reactants or the products by any number to balance the equation. If we had to do this, we would multiply the reactants or the products to balance the equation, but that would not change the E naught value. That value remains the same no matter what you do to the original reaction. But if we multiply the quote the reactants or the products, the N and the quotient Q will change accordingly, but the E naught will remain the same. So now we see something that looks like a typical exam question. They're asking us to calculate the voltage, or E, for the following cell, where iron solid is reacting in a solution of iron bromide, and that's going to produce bromine liquid. So below we see that we have two half reactions, where iron 2 plus is losing 2 electrons to become iron solid. We also have bromine liquid losing 2 electrons and going to 2 moles of Br minus. Now, the Fe2 plus reaction is going to be reversed later on to fit into the original reaction. So now we'll apply the Nernst equation, the simplified Nernst, because we always assume that we're at standard room temperature. So we have our reversed E naught value for the Fe2 plus. That's plugged into the first Nernst equation, and we have 2 electrons reacting. So we have the negative 0.44 minus the 0.05916 over the 2 electrons that we have. That's multiplied times the log of 1 over the 0.01 molar of the solution that the iron solid is in. That will result in an answer of negative 0.5. Now we'll take a look at the second half reaction, where we have our E naught value of 1.078 volts. We'll plug that into Nernst, and the same way we did with the first half reaction, we put the 0.05916 over the number of electrons, which is still 2, and we're going to multiply that by the log of 0.05 molar, and we're going to square that because we have 2 moles of Br minus. And when you plug that into the calculator, you're going to get 1.155. And because we had to reverse the Fe2 plus, when we solve for E, we reverse the value. So we see on the right-hand side, we see E is equal to 1.155, which is the E plus value that we solved for the second half reaction, minus the negative 0.5, and that is reversed. When you plug that in, you get a 1.65 volt E value. And because this value is positive, your electrons will flow from left to right in the normal fashion we think of, and this is going to happen spontaneously. So galvanic cell is basically the scientific term for a battery. Now, batteries are in just about everything from your laptop to your cell phone to the thing that starts your car in the morning, and they produce electricity because the cell, or the reaction, is not at equilibrium. When your cell is at equilibrium, where E equals 0, your battery is actually dead. So when the cell is at equilibrium, when E equals 0, Q also equals K. So we can change the Nernst equation so that our E naught value is equal to 0.05916 over N, which is the electrons, log base 10 of K. And then we can rewrite that so that K is equal to 10 to the N number of electrons times our E naught value over 0.05916. So electrochemistry has many uses, both in the analytical chemistry sphere, the biochemistry area, and also biology. So now we're going to talk about how this impacts biochemistry. Whenever H plus is involved in any redox reaction or ionic reaction we have, or whenever we have reactants or products that are either acids or bases, our reduction potentials are pH dependent. And this is because the standard reduction potentials apply to systems where all activities are 1. Now, we remember from the previous slide that an activity of 1 is nearly impossible to obtain. Because when we have an activity of 1, our pH would have to be 0, and that's nearly impossible also. And in any living system, our pH is usually close to 7, because we maintain homeostasis. So the activities are never equal to 1, and therefore our standard reduction potentials do not apply to most of our reactions. So in order to compensate for the difference in pH and the activities, most biochemists will use a formal potential, or E naught prime is what they call it. Now, formal potential is simply the reduction potential that applies under specific conditions. This can be either pH or ionic strength or any other conditions that you can see that would alter the reaction. And the formal potential at pH of 7, which is what our bodies is regulated at, is called E naught prime. And E naught prime simply takes into account the pH of the solution and will give you the most accurate value for that specific system at that pH value.